If you really need some help, okay, so we can schedule some kind of the office hour or the weekend, okay. So just send me email, okay. Yeah, if you have any questions, just type into the chat window, okay. Let's start, okay. All right, so like I said, kind of you have to determine SN1 and also yeah, the SN2 or E1, E2 reactions, okay. And then here, okay, primary, okay, and then that's very bulky base, okay. Normally I would list kind of region, okay, so on the top of the yeah, above the arrow. The bottom one just kind of solvent, okay, right. And then last here, the yeah, very bulky base only can work as base, not a nucleophile, okay. So this is actually therapeutic side, okay. So here, okay, so primary bulky base, okay, so that's E2, okay. So the E2 reaction, okay, so that's yeah, that's for that, okay. And then second one, okay, you see, okay, so that's yeah, become kind of ethoxide at the region, okay, so yeah, the yeah, attaching space, okay. So this is kind of strong base, but also strong nucleophile, okay, ethoxide, okay. So still primary and then strong base, strong nucleophile. Now it's kind of SN2 is kind of here the major product, okay. So that's here the yeah, product, okay. So make sure you know how to do it, okay. All right, and then yeah, the next one, okay, so yeah, that's secondary you can do SN1, SN2, whatever, yeah, anything, okay, so yeah, but here you need to look at kind of yeah, what's region here, okay, so this is kind of the yeah, sialate, okay, sialic sulfur compound, okay, that's here, okay, this guy, okay. So secondary and then sialate, okay, so SN2 reactions, okay, so that means here the yeah, when you draw the kind of yeah, substitution product, you have to kind of inverse the steric center, okay. Right, and then the next one, okay, so you see, okay, so the still yeah, same substrate, okay, but here the become kind of strong base, strong nucleophile, okay. This one, okay, and then secondary, okay, last year E2 will become a major product, okay. And then the major product, okay, so that's here, okay, so we follow science if we get more substitute arcane, okay. Right, and then falling case, so yeah, the still secondary case, but yeah, the yeah, still very strong base, okay, so strong base, strong nucleophile case, so yeah, that's actually kind of same as here, okay, so yeah, methoxide, okay, and then secondary strong base, strong nucleophile, and this one, okay, so yeah, the yeah, just make sure that the yeah, there are two kind of yeah, beta hydrogen, one's here, okay, so you put the down bond between this alpha carbon and this beta hydrogen, beta carbon, okay. Yeah, so we follow the safe, okay. Right, and then last one, okay, so that you can see kind of the tertiary one, okay, tertiary one, okay, no SN2 reaction, okay, and here's kind of the yeah, methanol weak nucleophile weak base, okay, right, and then tertiary one, okay, weak nucleophile weak base, okay, so SN1 reaction, so SN1 is major, okay, so in this case here the yeah, I'm actually gonna know this part, okay, so only OME, okay. So that's here the yeah, how do you use this chart finish here the yeah, questions, okay, for this type, okay. Right. All right, any questions? All right, if there's no questions, okay, we'll start your lecture today, okay. All right, okay, so although yeah, the lecture we cut today kind of the yeah, not yeah, be showed in kind of the yeah, quiz 2, okay, but yeah, I want you guys a little bit focus on, okay, because yeah, today's yeah, the lecture covers some kind of yeah, most difficult kind of reaction in chapter yeah, the 10, okay. So some involve some kind of a lot of their country, okay, so and some kind of a very special selectivity, okay. All right, okay. So last time we learned kind of how do you use the SN2 or SN1 reaction prepare alcohol, okay. So today we will study kind of yeah, how do we use the yeah, SN1 SN2 reaction prepare kind of ether, okay. All right. And then are yeah, really also similar like the yeah, kind of the alcohol, okay? So yeah, really depends on what kind of the ether do you want to prepare and what's the substrate, okay? So if it's kind of the methyl, okay, and also the primary substrate, okay, so yeah, you can use the alkoxide as a nucleophile, okay, and then directly do some kind of the SN2 reactions, okay, and then this reaction actually we call kind of the Williamson ether synthesis, okay. So yeah, that's the first name reaction we learned so far. Okay, so in future you will learn a lot of the named reaction. Okay, so by a different person's name. Okay, so yeah, Williamson ether synthesis. Okay, so this one actually kind of the SN2 reaction. Okay, right. So the general reaction. Okay, I show you guys here. Okay, still use the colored pen. Okay. Yeah, actually already showed the on the screen, okay. So pretty much you have alkoxide, okay, and then react with the substrate, okay. All right, substrate has kind of link group, okay, touch, okay, and a typical SN2 reaction process, okay. And after reaction, okay, so plus the link group, okay. And so this species, okay, so yeah, that's we call it kind of alkoxide, okay. Okay, so we already know that alkoxide kind of strong base and also a strong nucleophile. Okay, so yeah, in this case only happen to kind of the primary methyl. Okay, so that's for the SN2 reaction. So if you use this strong base for the secondary kind of substrate, okay, so we'll give kind of E2 elimination. Okay, so that's we just covered. Okay, and for this reaction, okay, so yeah, two things I have to need to be the keep in mind. Okay. But one thing is kind of normally we don't purchase alkoxide reagent, okay, so we prepare it from kind of corresponding alcohols, okay, and give you one example, okay, so yeah. All right, so yeah, we want to get kind of the propyl alkoxide, okay, so we from kind of the propanol, okay, and then the reaction actually pretty easy, okay, so yeah, just kind of add some kind of sodium, okay, sodium kind of metal, okay, so yeah, careful control, make sure there's no water, okay, solely add it in, okay, and then cool in kind of ice bath, okay, and then stir a little bit, okay, so eventually kind of sodium will all dissolve, okay, and then during this process, okay, so you generate kind of the alkoxide kind of sodium salt, okay, and meanwhile, okay, hydrogen become kind of gas is gone, okay. So that's how they prepare it. Okay, so I did some kind of these reactions. Okay, so yeah, kind of pretty interesting. Okay, and after the reaction is done. Okay, so yeah, this is kind of the propyl group. The alkoxide. Okay, and also in the propanol. Okay, so yeah, then you just kind of use same system as substrate. Okay, for example, here we use the ethyl iodide. Okay, and then after reaction. Okay, so SN2 reactions. Okay, and then just kind of put ET here. Okay. And so if you use some kind of the weak some kind of other the more acidic the alcohol, okay, like phenol, okay. So even you don't need use some kind of sodium, okay. So you just kind of rubber base kind of deprotonated, okay. So okay, we want another example, okay. Yeah, phenol, okay. So phenol kind of the pK, this one is probably 9, okay. So yeah, more acidic, okay. So in this case here, you even use kind of the potassium the carbonate, okay, you can deprotonate it, okay, and then generate kind of corresponding kind of the alkoxide, okay. Right. And then you just kind of apply some kind of substrate, okay. So for example, we use kind of methyl iodide, okay, and then after reactions, okay, SN2 reactions, okay, so kick off your iodide, okay, and then generate kind of methyl group here. Okay. All right. And another important thing for this reaction can make ether case, yeah, you have to be careful, okay. So we have for the unsymmetrical ether case synthesis, okay. So which one you use as kind of the alkoxide and which one you use substrate, okay. So what's that mean? Okay, give you one example, okay. All right. So for example, I want to make this ether, okay. So one branch is kind of ethyl group, another branch kind of the isopropyl group, okay. All right. What do you mean? Oh, the hydrogen goes to air, okay? It become gas, okay? It's gone. All right. Okay, so yeah, here's kind of ether, okay? We want to make this ether, okay? So we can have two pathway, okay? All right. So these arrows kind of show the retrosynthesis, okay? So we showed kind of what starting material okay, used to make this the product, okay? So one kind of we can use this ethyl part as alkoxide, okay? And then react with the isopropyl part as kind of substrate, okay? Some kind of link group here, okay? Another kind of we can use this isopropyl part okay, as alkoxide, okay? And then react with the ethyl group as kind of the link group, okay? Right. So it looks like here the both can work, okay? So SN2 reaction, okay? So but reality only one is working, okay? Which one is working? The top one or bottom one, okay? Type in your chart window. Where someone said top, okay? Any other suggestions? Another one. All right. No one gave me right answer, no. Right. The bottom one should be right, okay? That's true. Why is that, okay? That's right, okay. That's what we bring back here, this guy, okay? All right, so this is kind of strong base, strong nucleophile, okay, as oxide, okay, and then this is secondary, okay. Look at here. Strong base, strong nucleophile, second straight, okay. So what's the major product, okay? Okay, E2, okay. So you won't get kind of the SN2 product, okay. So for reality, this reaction generate kind of this major product, okay. Never can give kind of the substitution product as a major product, okay. Got it, okay? Okay, so that's the key thing, okay. So that's kind of important top point, okay. So if you want to make here this unsymmetrical the ether, okay. So keep in mind, okay, the substrate, okay, substrate, okay. So always kind of primary substrate, okay. Right, primary substrate, okay, that's here, okay. Okay. So if you use the secondary, okay, so that's the E2 emission, okay, will happen, okay. So get it, okay. So normally for the base, it doesn't matter, okay. So even kind of strong base, strong nucleophile, okay, primary substrate, okay, so still give kind of the SN2 major product, okay. All right, so that's why I said kind of one of the difficult one for this today's lecture, okay. All right, and then we move to kind of another substrate, okay. So another kind of the So if we have to use the secondary or tertiary substrate, okay. So what's here the reaction we can go in on? Okay, so that should be 2 here. Yeah. So if you have to use kind of the secondary or tertiary kind of substrate, okay, then you have to go through kind of S1 reactions, okay. So S1 reactions, okay, so you cannot use so strong kind of the nucleophile, okay. Then we have to use kind of weak nucleophile, weak base, okay. So that's the definitely kind of the alcohol, okay. All right, so I draw you kind of general reactions, okay. All right, okay, see here, okay, that's alcohol, okay. All right, and then once your reaction done, okay, you generate kind of the corresponding kind of ether, okay. And normally kind of OH okay pick up here the HC the air, okay. Yeah. So that's here the whole process, okay. And so give you one example, okay. Yeah. So T-butyl, substrate, okay. So T-butyl bromide, okay, and then react with the ethanol, okay. Weak base, weak nucleophile, okay, and then you generate kind of the ethyl ether, okay. Okay, and if you want to draw another byproduct, that's fine. Okay, normally not required for the class, okay. Right, so normally speaking, okay, so yeah, this reaction kind of should work, especially for the kind of the tertiary substrate, okay. But for the secondary substrate, okay, so yeah, that's the little bit kind of challenge, okay. So so either in the question, what's the product we're looking for? Yeah, that's right, okay. So the question here, okay, so yeah, whenever I show this kind of arrow means kind of this is product, I want to show kind of the region, okay. So that's one type of question showing kind of organic chemistry, okay. So we call it kind of synthesis design questions, okay. All right, okay, so but yeah, we go back to secondary tertiary, okay. So normally speaking, kind of tertiary is okay, so you can still get kind of decent amount of your product ether, okay. But secondary kind of normally get kind of somehow poor yield, okay. So in this case, some people, even some ways, okay, try to put equilibrium to the right, okay. So yeah, just add some kind of silver nitride, okay. Okay, and then you use kind of alcohol, okay. Right. So what happens kind of you start with still alkyl halide, okay. So normally we use alkyl halide, okay. So can be chloride, okay, or bromide or iodide, okay, and then you use these reaction conditions, okay. So we do apply here, okay. All right. So once reaction is down, okay, so you generate kind of the ether, okay, and then plus this silver, okay, will pick up kind of chloride bromide, okay, generate kind of silver kind of the chloride, okay, or silver kind of bromide, or silver kind of iodide, okay. So those kind of if you took organic chemistry, not organic chemistry, general chemistry, okay, so has very poor solubility, okay, it's still precipitate out, okay. Okay. So in this case, can push equilibrium to the right, okay. So yeah, that's the way, how do you kind of speed up this reaction, okay. So that's if you without kind of silver nitride, okay, so somehow kind of equilibrium, okay. But if you add this one, okay, you precipitate out kind of the leaving group, okay, and then push equilibrium to the right, okay. All right, so that's the second way kind of prepare alcohol, okay, so prepare ether, okay, based on kind of secondary and tertiary substrate, okay. So keep in mind, SN1, okay, you use alcohol, okay. All right, so now we move kind of the new reaction, okay. So yeah, that's actually kind of we haven't learned any mechanism for this reaction, make here the ethers, use alcohol condensation, okay. So that's also one of the most difficult reaction for these chapters, okay. So what happens kind of this time we don't use any kind of acid, don't use any kind of nucleophile or kind of the base, okay. We do the reaction under the acid condition, okay. Just kind of use one alcohol, okay. So pretty much just kind of two same alcohol molecule, okay, and then under the acid conditions, okay, and then these two condensed, okay, generate kind of alcohol, symmetrical alcohol, okay. And then meanwhile, okay, so you can release the water, okay, so okay. So for this reaction, okay, so one thing just keep in mind, okay, so so you use acid as catalyst, okay. So normally kind of sulfuric acid, okay, occasionally you can use the HCl, okay, so sulfuric acid kind of the best, okay. And also second is kind of only be used to prepare symmetrical kind of ether, okay. Right. So that's these two molecules have to be same, okay. So if you get kind of two different alcohol, can mix them together, okay. So you can get all the five, actually three possible products, okay. So for example, you have OHR1, okay, plus the two, okay. So you want to kind of apply same conditions, okay. So you can get kind of three products, okay. So R1, okay, and then plus kind of R1, R2, okay, plus R2, R2, okay. So that's kind of the useless, okay, because they got kind of mixture, okay. All right. Okay, that's something keep in mind, okay. All right, more important kind of the reaction mechanism, okay. So here you have to draw it with me, okay. All right. So it's really depends on what's your substrate, okay. So if you kind of primary kind of substrate, okay, Spermine alcohol, okay, and then that's actually follow SN2 reaction mechanism, okay, right? I'll draw for you, okay. So pretty much I use propanol, okay, as a kind of example, okay, right? Right. First step, okay, so remember OH group kind of very pooling group, okay, and then you have to convert OH group to good group, okay. So that's why we use acid, okay. So protonated kind of OH group, okay, convert to kind of water, okay. Right. Okay, so this water cannot live by itself, okay, because this primary carbon cation not stable, okay. So you have to get another alcohol, okay. Right, push it away, okay. So another propanol coming in, okay. Slow down, please. Okay, okay. I will try to slow down. All right. Yeah. All right. Do you guys got here? Okay. So if you want to do the kind of the alcohol condensation, okay. So acid conditions, okay. Same kind of the alcohol, same alcohol, okay. So two same alcohol molecule, okay. All right. And depending on what's here the substrate, okay. So if primary alcohol, okay. So that's primary alcohol, okay. So you do it kind of SN2 mechanism, okay. SN2 mechanism, okay. So that's here, okay. First alcohol pick up proton, convert here the link group to water, okay. And then second alcohol come in, okay, as nucleophile, okay. So this one attack here and push away kind of the link group, okay. Yeah. All right, and then what you generate something like this, okay. All right, and then positive charge here. And then that's just don't forget, okay, because the OH coming in, okay, so the hydrogen still on oxygen, okay, so you have to a little bit the base, okay, coming in. So the base is just pretty much just gonna water, okay. Yeah, because you lose one water here, okay, so you lose water. All right, so this water will kind of pick up this hydrogen and then shift back, okay, and then eventually give you kind of final the alcohol, okay, ether, okay. Yeah, so that's here, okay. Right. So that's SN2 reactions, okay. Keep in mind, okay. So that's here the SN2 step, okay. Right. Okay, so if it's kind of secondary and tertiary alcohol, okay, you want to do the kind of the alcohol condensation, okay, and then that's actually kind of follow S1 reaction, okay, S1 reaction pathway, okay. And then what happens kind of you still do the same thing, okay, protonated kind of OH group, but then OH group live by itself, you generate kind of carbon cation, and then the alcohol coming, okay, so neutralize it, get kind of final kind of ether, okay. So again, I will show mechanism, okay, please draw it with me, okay. So this time I use the T-benzyl alcohol example, okay. Why does the water pick up the proton, want to make it more? Okay. All right. So that's why I said kind of the acid catalyst, okay. So you see here, okay. So let's pick up the hydrogen, okay. Use one the protons, okay. But eventually, okay, the proton can be picked up by the solvent, okay. You release the H, okay. So that's kind of can be reused, okay. So yeah. Okay. So acid kind of won't consume during whole process, okay. So and then you can reuse, okay. So relatively speaking, this is kind of a strong acid, okay, strong acid, okay. So because proton on here, okay, and then that's why acid-base reaction happens, okay. Water pick up the protons, okay. You from strong acid, then kind of weak acid, weak base, okay. Yeah. All right, okay. So now we continue for the secondary and tertiary kind of alcohol, okay. So same thing, okay. So pick up the protons, okay, and convert the OH group to kind of the beta link group, okay. All right, so this time, okay, so water can live by itself, okay, because kind of that's you can generate kind of more stable kind of tertiary carbon cation, okay. Okay, that's different from kind of SN2 reaction, okay. All right, and then second alcohol coming, okay. All right, neutralize it, okay. All right, so that's the give you similar like this, okay. So the hydrogen still on oxygen, okay. Keep in mind hydrogen still on oxygen, okay. So similarly, this guy, okay. Right, and then the water, okay. So the left water, okay. So coming back, okay. So acid-base reaction, water will kind of a weak base, okay, and then pick up your protons, okay, and then eventually give you kind of a final product. Okay. So that's kind of distributed kind of ether, okay. All right, got it, okay. Make sure you know how to draw the mechanism for the alcohol condensation, okay, because that's kind of one of the required mechanisms, okay. All right, so again, primary SN2, okay, secondary tertiary SN1 reactions, okay. So theoretically speaking, okay, so I will say kind of this way kind of relatively easy for the primary alcohol make kind of ether, okay, and then for the kind of secondary tertiary kind of there will be some kind of competing reaction, okay. So yeah, that's what I'll talk about later, okay. E1 reaction, okay, and then actually kind of got a mixture, okay. Yeah, you have to really control the reaction conditions, okay. All right, okay, so now we move to another hard part, kind of make a cyclic ether, okay. So intramolecular reactions, okay. So that's the alcohol condensation, okay. So now we move to a full, okay. Cyclic ether, okay. So cyclic ether, yeah, the formation we already learned a little bit in the chapter 9, okay. So yeah, remember, okay. So yeah, similar one, okay, probably, okay. So you have one nucleophile and then yeah, link together with the link group by a long carbon chain, okay. So two functional group, okay. So yeah, that's yeah, you can have kind of intramolecular reactions, okay. All right, so click off, okay. So you generate kind of yeah, fine membrane, okay. Yeah, so that's your cyclic ether, okay. All right. So remember, okay. So for cyclic ether, is 3 membrane, okay, 5 membrane, and 6 membrane kind of yeah, preferred, okay. So. All right, okay, cyclic ether, okay, so yeah, yeah, you have to little bit careful about kind of stereochemistry, okay, so especially kind of make yeah, 3 membrane actually another name called kind of yeah, epoxide, okay. All right, give you one example, okay. Okay. All right, so we have this starting material, okay, and you find all that's the yeah, nucleophile, okay, here, okay, OH, and then that's the link group, okay, Br. All right. Okay, so then you want to do some kind of yeah, SN2 reaction, ring closing, okay, so you apply some kind of base, okay. Deprotonated kind of this hydrogen, okay, this become kind of O minus, okay. But keep in mind, okay, SN2 reaction, okay, so you have kind of nucleophile attack from back of the link group, okay. So in this case, okay, so you have to rotate this bond, okay, and then generate kind of the yeah, ideal conformation for the yeah, SN2 reaction. So that's O minus now, okay. Should be here. Okay. So once you still wedge bonds, sorry, yeah. So this one become ET, okay, and then hydrogen should connect by wedge bond, okay, and then Br. Okay. So the ET, okay, as a group connects by kind of yeah, dash bond, okay, and then yeah, this one, okay, some questions. How do you name the E? So naming for the cyclic ether normally are not required, okay, so yeah, don't worry about, okay, so just kind of yeah, that's fine, okay. The oxygen is attacking the water carbon, okay. Okay, so this carbon for the top one, okay. Right, so for the bottom one, okay, I will show you, okay. Right, so you have to make sure the oxygen kind of the link group kind of yeah, somehow anti-covalent, some like the yeah, E2 elimination, okay, but this is kind of substitution reaction, okay. All right, okay, so now yeah, you can do SN2 reactions, okay. Click off, okay. Right, so after reaction, okay, so for the real product, okay, so like something like this, okay. Hydrogen, math, okay, and then you'll see kind of the ET is kind of dash bond, and then the hydrogen here is kind of the wedge bond, okay. Okay, and if you line the steric centers, you find kind of for starting material, okay, the left one kind of R and the right one should be S, okay, but after reactions, okay, so this is R, this is also R, okay. So that's exactly the same as kind of SN2 reaction, okay. So yeah, you kick off link group, okay, you inverse the stereochemistry, okay. So yeah, here, okay. So that's be careful, okay. So yeah, in exam quiz, okay. So if I show you some kind of starting material, ask you to do some kind of the 3-membered kind of the ring, okay, formation, okay, cyclic ether formation, okay. So you don't directly do it. You have to make sure kind of OH kind of the link group kind of on opposite side of this kind of the bond, okay. So that you can do it, okay. So rotate the one of the bond get kind of product, okay. Right. And so that's give you another example about the stereochemistry, okay. Right. Right. So we try to do some kind of the intramolecular kind of the ring closing reactions, okay, make some 3-member ring, okay. So yeah. So show the kind of two starting material, okay. So which one can give me kind of the product in high yield, which one very slow reaction, okay. Can anyone tell me kind of just type in kind of the which one kind of the slow reaction, okay. Slow one, okay. Just type the slow one, okay. Yeah, that's right, okay. Right one will be slow, okay, because both nucleophile link group kind of collect by wedge bond, okay. So that's no matter how do you do ring flip, okay, never can reach the kind of this anti-coplanar, okay, back attack positions, okay. But for the last one, okay, so no problem. One kind of dash, one wedge, okay, you do ring flip. There are certain situations, okay, so you can reach kind of both kind of the transaxial, okay, you can close the ring, okay, and then you generate kind of product like this, okay. Okay, so that's the still kind of remembering. Okay, so this one kind of slow. Okay, slow reaction. Okay. Okay, so that's pretty much we use kind of the base and also the alkoxide, okay, to the reaction, okay, to make it a cyclic ether, okay. So you can also use alcohol condensation, okay, so yeah, to do the reactions, okay. So give you one example, okay. So still intramolecular reactions, okay. All right. So we have this diol, okay, a 2OH group, okay. All right, and then we use some kind of strong acid, okay, sulfuric acid, okay, and then after reactions, okay. Yeah, we generate kind of the final product, okay. So this one, okay, so yeah, first question for you guys, okay. So for these reactions, okay, it's SN1 reaction or SN2 reaction? So, that's a kind of alcohol condensation. Type in chart window SN1 or SN2 reaction. Last one, okay. Yeah, perfect. Okay, SN1. Okay, that's right. Okay, you guys didn't forget. Okay, so here, secondary and tertiary alcohol. Okay, SN1 reactions. Okay, and here. Okay, so yeah, that's here the tertiary secondary. Okay, so that's SN1 reaction. Okay, all right. And then second. Okay, so question for you guys. Okay, so yeah, we have two alcohol. Okay, so which alcohol as nucleophile? Which alcohol as kind of link group? Okay. Type in chart window, okay, so you can select kind of left nucleophile and then right kind of living group, okay, or right kind of the living group, kind of left kind of nucleophile, okay. Yeah, that's right. Okay. Yeah, that's right. Okay. So after the link group, okay, because this is kind of SN1 reactions, okay, and then the last one, yeah, generally kind of the more stable carbon cation, okay. So you generally kind of the water, okay, you get off, okay. So that's the rate limiting step, okay. And then you generally kind of the tertiary carbon cation. If you write one, okay, so that's will be kind of the secondary carbon cation, no stable, okay. So this is kind of link group, okay. So and then link group, okay. And then the right one is kind of nucleophile. Okay, pretty good, okay. All right, okay. So now we move to even harder kind of reaction, okay. Get a new paper. Right, so reopening of epoxide, okay. Yeah, we try hard kind of make a three-membered kind of the cyclic ether, okay, but now we try to open it, okay. So just kind of concept kind of information, okay. So three-membered kind of cyclic ether we call kind of epoxide, okay. And its common name, okay. So yeah, if you read some kind of the old the literature, it's also called kind of oxyrin, okay, oxyrin, okay. So for the epoxide, okay, because the bound down go close to kind of 60 degrees, okay, far away from kind of the idea kind of sp3 hybridized kind of the bound out, okay, 109.5, okay. So make them kind of very reactive, okay. So than any other ethers, okay. So it's easy to open the kind of ring, okay. So the overall reaction, yeah, pretty much it happen like this way, okay. So we have an epoxide, okay, and then some nucleophile, okay, come in, okay. Yeah, attack kind of one of the carbon and open the ring, okay, and then you generate kind of something like this. And then yeah, normally you can do the workup or kind of O minus pick up some solvent from pick up the H plus okay, from solvent, okay, and then give kind of the alcohol, okay. Yeah, so that's the overall reaction, okay. You convert epoxide into alcohol, okay. All right, someone maybe ask me, okay, so you said kind of the OR group kind of were pooling group, okay. So that's OR, okay. OR minus kind of very strong basically. How come you kind of kick off the OR group Catholic group, okay? A reason for that kind of because that's kind of special case, okay. Very strong ring string, okay, and then you want kind of release this ring string, okay. Last push reaction happened, okay. So that's it's very special case, okay. All right, and then we come kind of tricky thing for this reaction, okay. So for the ring opening of the epoxide actually can happen under kind of basic neutral condition and also acid condition, okay. So these two conditions actually kind of follow different mechanism, okay, and a little bit kind of the different in their kind of regional selectivity, okay. So yeah. All right, so we first do basic and also neutral condition, okay. So right. So yeah, if you have kind of some kind of the base, okay, as a nucleophile, okay, so yeah, and some kind of basic species, okay, and then yeah, this the base, okay, if we have kind of unsymmetrical kind of epoxide, okay, and then it's you open kind of attack kind of last substitute kind of carbon, okay, right? So yeah, normally you can have target right or kind of left, okay, either carbon, okay, but this kind of follow SN2, okay, attack last substitute, okay, because the stereo hindrance, okay, and then also attack from back, okay. So that means kind of both regional and also stereo follow kind of SN2 reactions, okay. So maybe Joe, you guys kind of a little bit more, yeah. So that's actually kind of pretty much the same thing, okay, just show you in kind of wedge bond structures, okay. Right, so we have this the epoxide, okay, right, and then one carbon, okay, so it's kind of two methyl group, one carbon has only one methyl group, okay. So in this case, when nucleophile come in, okay, want to attack a last substitute carbon, open like this way, okay. OC3, okay, and then this the oxygen just kind of pick up protons, okay, and just gonna go ahead and draw the final product, okay. All right, so once it's done, okay, so yeah, if you look at kind of stereochemistry, okay, so yeah, this one original kind of ISK after reopening, okay, become R, okay, typical SN2 reactions, okay. So that's why we said kind of this reaction kind of neutral and also basic conditions, okay. So stereochemistry follow SN2, okay, inverse stereochemistry, okay, and also regiochemistry also follow SN2, okay, attack last substitute carbon, okay. Right, and then now we come kind of acid conditions, okay. Acid condition kind of now the story a little bit different, okay. All right, so acid condition, okay, so the nucleophile still attack from back of carbon, okay, but will attack kind of more substitute carbon, okay, more substitute carbon, okay. And in other words, kind of stereochemistry still follow SN2, okay, so back attack, okay. But here will attack kind of last substitute, more substitute carbon, okay. So that's actually follow kind of SN1 like here more substitute, okay, like tertiary followed by secondary, don't like kind of primary, okay, right. So why is that, okay? So I draw you guys kind of mechanism, okay. Yeah. So I use yeah. This epoxide example, okay. So you can see kind of there are two carbons, okay. The one has no substitute it's kind of just two hydrogen here, okay. So the another carbon, one methyl, one hydrogen, okay. Right, and then let's pick up the hydrogen, okay. So that's acid condition, okay. Pick up hydrogen first, okay. Right, and then you can generate kind of two intermediate, okay. So once you pick up a hydrogen, okay. So one is something like this, okay. Yeah, we still put hydrogen on, okay. So just right. So somehow kind of oxygen, okay. So with the right carbon kind of bond break up, okay, and then the positive charge on oxygen can share with the right carbon, okay. Another intermediate, okay. Right. Somehow kind of oxygen with kind of left carbon kind of bond break up, okay, and then somehow kind of this positive charge shared with kind of the left carbon, okay. Right, so that's casing, okay. So we have to compare which one's more stable, okay. So remember, this one a little bit close structure to carbocation. Carbocation kind of more substitute, more stable, okay. So that's here have kind of the methyl group here, okay, and then here nothing, just hydrogen, okay. So that means here this one being, okay. So that's more stable intermediate, okay. Right, more stable intermediate, okay. So that means kind of this right carbon has the positive charge on it, positive charge on it, okay. So if right carbon has positive charge on, okay, and then the nucleophile come in, okay. So for example, this reaction with down kind of in HBr, okay. So, and then Br coming, okay, Br, okay. So Br a little bit negative charge, okay. So like to the positive part, okay, and then goes here, and then you open the ring like this, okay. And eventually, okay, so you generate kind of the R core like this. Hydrogen and then Br. Okay. So that's why kind of like I said in the very beginning, okay. One more time. Right. So reason for that kind of once you pronate kind of the oxygen here, okay. So you can have kind of either the partial positive charge on the left carbon or kind of on the right carbon, okay. But here normally speaking, kind of positive charge on the kind of more substitute carbon, more stable, okay. So like here the tertiary carbon cation, okay. So do this. Tertiary carbon cation more stable than kind of secondary carbon cation, and then much more stable than primary carbon cation, okay. Yeah. Okay. So that's just similar reason here, okay. this kind of more substitute, more stable kind of this you can treat this one as kind of probably the tertiary carbon cation, okay, and this one as kind of secondary carbon cation, okay. So this one more stable, okay. So that means kind of positive charge want goes here, okay, and then if the positive charge go here, okay, nucleophile normally kind of negative charge, okay, and then positive like negative, negative like positive, that will go kind of here, okay, and open ring like this, okay, right. So for you guys, if you still don't understand what's going on, okay, just keep in mind, okay, so the nucleophile, if it's kind of the ring opening reaction down kind of basic conditions, okay, so nucleophile attack kind of last substitute carbon, okay, so you can acid condition attack the most substitute carbon, okay, so both kind of the back attack, okay. Right, give you one example, okay, probably you will get it, okay. Right, so we have this epoxide, okay. And then this is oxygen, okay, so right, so that's oxygen, and then connect by kind of the wedge bond, okay, and then kind of the dash bond connect with the methyl group, okay. Right, okay, and then if we want to do kind of a ring opening reaction for this epoxide, okay, so we can do either acid condition, okay, so let's try use the methanol as kind of the nucleophile this time, okay. Oh yeah, we can use kind of do it kind of basic condition, okay, so in this case we use methoxide, okay, give kind of totally different product, okay. So if the acid conditions, okay, so still OMe as a nucleophile, okay, but keep in mind, okay, so acid condition like a more substitute carbon, okay. So that means here eventually this guy will attack here, okay. And also keep in mind, okay, so the back attack, okay, so you inverse their chemistry, okay. So once you're done the reaction, okay, OMe become kind of the wedge bond, okay, and then this methyl become kind of the wedge bond, okay. OMe dash bond and methyl wedge bond, okay, and then the ring open like this way, okay, and then OH, okay. So that's still wedge bond, okay. But if it's kind of under a basic condition, okay, so basic conditions, okay, so I use different color, okay. We'll attack last substitute carbon, okay, and then open the ring like this, okay. Also, again, back attack, okay. Right, back attack, okay, so that means here the OMe kind of the dash bond, okay, and then if you open like this way, okay, so another carbon has nothing to change, okay. OH. Okay, so you see kind of a difference, okay. Acid conditions, okay, nucleophile attack now more substitute carbon. Basic condition, nucleophile attack last substitute carbon, okay. But both reaction conditions, okay, back attack, okay. So that's why kind of both become kind of the dash bond, okay, dash bond, dash bond. Right. So that's probably the most difficult kind of the part for the chapter, chapter 10, okay. So reopening of the epoxide, okay. All right, so one small practice, okay. Actually, kind of this one you can do it when you go home, okay. All right, so we have this epoxide, okay, and then we want to do some kind of the reopening reactions, okay. One kind of acid kind of conditions, okay. So acid condition, okay. So we use kind of just water as a nucleophile, okay. Acid condition, okay, water, okay. Another kind of basic neutral conditions, okay. So we use sodium azide as a nucleophile, okay. Right. So try to draw the product, okay. Try to draw the product, okay. Yeah, that's right, okay. So inversion of your chiral center, okay. So if you are the carbon kind of chiral, okay, it will inverse the case. So you can learn R and S, R become S, S become R, okay. So So no matter acid-base condition, okay, always inversion in the center, okay. So the stoichiometry for both condition, acid condition or basic condition, same, okay, stoichiometry, okay. A difference in kind of regiochemistry, okay, regiochemistry which carbon, do you attack, okay. So so that's why I showed here, okay, the slide, okay. So for both, the stoichiometry, okay, back attack, okay. But here regiochemistry, okay, so acid condition, okay, SN1, okay, basic condition, okay, SN2, okay. Upon the left, okay, N3, okay, nitrogen oxide, okay. N3, okay. So this is kind of we can treat as kind of neutral kind of nucleophile, okay, neutral condition, okay. Neutral condition same as kind of basic condition, okay. So this is acid condition. All right, so try to practice on this one, okay. So I will go through the answer for this one, okay, in the class next time, okay. So make sure that you first find out where the nucleophile goes, okay. So left carbon or right carbon, okay. And then second, okay, so you have to show kind of your stoichiometry, right, okay. Back attack, okay, keep in mind. All right. Okay, so any question for the class today? Stop the recording.